All right, so I'm just going to make this a video of this whole section again, just to have it all together. So those of you who are in class, just go ahead and skip ahead to where we left off or where you need to look at. All right, so in section 14.6, it's about directional derivatives and the gradient vector. So if you just read through here real quick, so it says how when you have a map and it has the temperatures on it, this kind of look like those, like the level curves that we were looking at before. So of course, like along here, the temperatures come together 60 degrees, and the green part is 50, and so forth. And so if you were at, say, Reno, and you wanted to know how the temperature is changing, if you did the fx, the temperature, the derivative with respect to x, then you would be knowing the temperature change in this direction, right? So then if you did ty, you would know the temperature change with respect to this direction, like north, right? And east for the other one. So, but you don't always want to go north or east. Like sometimes you want to go in this direction, or maybe you want to go northeast or whatever. So you have to have a way to come up with a derivative in a certain direction. And so that's what the directional derivative is. So anyway, here we go. So fx and fy represent the rate of change in the x and the y directions. So we can use these to find a tangent plane, of course, like we did before. And that a tangent plane to a point that's determined by the changes in the x and the y directions. So that's at a certain point of a tangent plane. But if we want to go in a different direction, then we need what's called a directional derivative. Right? So our goal is to find the rate of change of z at a certain point in the direction of any unit vector. So it's important to remember unit vector. So the length of the vector is 1. So if it's not a unit vector, remember that you have to divide it by its own magnitude to make a unit vector. All right, and that unit vector is going to be called u. Right. So below is how we do it. The notation for the directional derivative is right here. So that is directional derivative, I guess you could say with respect to u, because that's the direction you're going in, and of f of xy. So here's what we do. So du of fxy is going to be this. You have the derivative of your function with respect to x, and you are multiplying it by a, the first part of your u vector, plus the derivative with respect to y, and multiplying it by b. Well, when you do this, if you notice, this kind of is like a dot product. It's kind of like you did fx and fy. If that was a vector, you dot producted it with vector ab. All right, so you can see how it breaks up into the dot product. So we are going to call it that. So it's a dot product, so we got fx comma fy dotted with u, basically. Okay, so this is our definition of our directional derivative. All right, that's a little ugly. Hang on. All right, so we're going to go ahead and do that work down here. So to do this, if I want my directional derivative, I want it at the point 1, 2. So I'm going to need my fx and my fy. So fx, here's my function here. I got 3x squared. This 4y squared is going to go away, but then the derivative of the middle section would be negative 3y with respect to x. Then for fy, the extra third is going to go away. The derivative of the middle section is going to be negative 3x, and then plus 8y. So we have to do these at the point 1, 2. We're going to want those at. So if I plug in 1 and 2 into the top part, I get negative 3. And if I plug 1 and 2 into the bottom, I get negative 3 plus 16, so 13. All right, so I was also told here, it says in the direction of pi over 6. So now remember that when somebody tells you in the direction of pi over 6, you're getting that from the unit circle. So pi over 6, the point on the unit circle there is square root 3 over 2 and 1/2. And so really that's already a vector, because you're going this much in the x direction and this much in the y direction. So it's really the vector radical 3 over 2 and 1/2. And since you're on the unit circle where the radius is 1, it's already length 1. And so it's perfect, and you use your unit circle values. So if I want my directional derivative of the function at 1, 2, it is going to be this negative 3 and 13 vector dotted with radical 3 over 2 and 1/2. All right, so you put those together, add them together, you get negative 3 radical 3 over 2 plus 13 over 2. Okay, and so it's just a number, so that is your derivative, your velocity, going in that direction at that point. All right, so this function right here. So let's see, there's supposed to be an f right there. So same process, my coordinate is radical 2 over 2 and radical 2 over 2. All right, so let's see, my fx, now this looks horrible, but not that bad. Remember, this is like having a 1/2 power. So my derivative is 1/2, 1 minus x squared over 4 minus y squared over 9, put back to the negative 1/2. Now times the derivative of the inside with respect to x. So that would be the derivative of this part right here. So I'd get negative 2x over 4, so I'm going to say negative 1/2 x. All right, and then fy is going to be the same thing. 1 minus x squared over 4 minus y squared over 9 to the negative 1/2, but times negative 2/9 y. All right, we had to plug in 0 and 2 for these. So in class when we did this, I made everybody kind of do this one. Anyway, so when I plug in 0 and 2 in the top one, notice I have this x right here, so that makes the whole thing go to 0, so that's lucky. But down here, I'm not so lucky. I end up getting 1/2, 1 minus, I get 0 for the middle, and so then I have 9/2, so that'd be 4/9 to negative 1/2. And on the outside, I have negative 2/9 times 2, so negative 4/9. All right, so clean this up, and I end up getting, let's see, this cancels out to a 2, so I have negative 2/9 on the outside. On the inside of that, negative 1/2, I have 5/9. So a fraction gets flipped over, so I have negative 2/9 times, flips over to 9/5 and do the square root, so that would be 3 over radical 5. So by the time I'm done, I have 3 goes into 9 3 times, and I have negative 2 over 3 radical 5. All right. Okay, so this is my fx, fy vector. So I am doing 0, negative 2 over 3 radical 5, dotted with radical 2 over 2 and radical 2 over 2. So I'm finding my directional derivative of the function at 0, 2. In the direction of 45 degrees. Okay, so the first multiplication is easy, that's 0. And for the second one, the 2's cancel out, so I get negative radical 2 over 3 radical 5. And you could rationalize it or whatever, or just leave it like this. Okay, so the gradient vector. The vector that we used earlier in our directional derivative, meaning this one right here, fx and fy, is a vector that we use in many, many places, so it gets a special name. It gets named the gradient of f. And it has a special name, so that's this guy right here, fx and fy. And its notation is this, upside down triangle. So a regular triangle would be like delta f. Well, this one is called del f. So you say del f, so del f of xy, or you just say del f. You can write it like that. Okay, so this just has a special name. It's just a vector with the 2 derivatives in it. Okay, so if somebody wanted you to find that, then you'd say, okay, find del f at 0, 1. So all that means is find fx and fy, put it in a vector, and plug in 0, 1. So my derivative with respect to x here would be cosine x plus e to the xy times y. Derivative with respect to y would be 0 for sine, and then e to the xy, but times x. All right, and plug in 0, 1 into those. Would get me, let's see, cosine at 0 is 1 plus 1 times e to the 0 is 1, so that gets me a 2. Over here, I have an x in front, so the whole thing's multiplied by 0. So I basically have this answer, my del f at 0, 1. So my gradient vector at 0, 1 is the vector 2, 0. Okay, so since we now have a special notation for the gradient vector, that was part of our directional derivative, we can rewrite the equation for the directional derivative. So remember this old formula over here, this guy right here. So if I rewrite that a little bit, I can move this over so that I have like this piece, these pieces over here. So I have basically that the dot product is equal to magnitude of u times magnitude of v times the cosine of theta, right? Like if I kind of rearrange that. So this is also a formula for the dot product. So let's take what we did earlier. Remember our du of f of xy, our directional derivative of the function at xy was simply del f dotted with u, right? So remember from before, that's what we're like basically going back to this, right? Because this is now the name, this is del f now. Okay. All right. So it's a dot product. So I could kind of use the same phrasing as over here for the dot product. The dot product is the magnitudes of the items times the cosine of the angle between them. So remember, this angle is the angle between u and v. So in my case, it'll be between del f and u. So I'm going to put magnitude of del f, magnitude of u, cosine theta. All right, so this guy right here, the magnitude of u, well, u is a unit vector, so that's just 1. So this is just 1. So basically, I have the magnitude of del f and the cosine theta. Now remember, theta, this is not hard, not easy to find. A lot of times in these problems, you're given, go at this angle. So it's not necessarily that angle. You have to find the angle between your directional derivative and where you're going. So you're not always just straight out given that angle. So you can't just always use this formula, but it's going to do something else for us in a second. All right, so this is the angle between del f and u. Okay. All right, so this is a formula that we came up with, right? So this is a fixed value, right? This is always going to be the same, like the magnitude of the of del f at whatever point you're at. Okay, so that's not going to change. What's going to change about your directional derivative here is the cosine, right? So this is equal to the directional derivative. So the cosine will change, like depending what angle you're going with, or what angle is between your u and your del f. So I just want to point out that when is cosine the largest? Well, cosine, if you think about the graph, the largest it is when it's 0. So cosine of 0, so when theta equals 0, then cosine of 0 is 1, right? Because it starts up at 1 and it goes down like this and across. So when is cosine the least? Well, that's at pi. So when theta equals 180 degrees, or pi, then cosine of 180 is negative 1. Right? So depending on the value of the cosine, depending on the angle that you're trying to go, like the angle between your two things that you're trying to do, this number will vary, but this will always stay the same. And so let's say del f, the magnitude of del f is like 5. So if you are going at a 0 degree angle, so if you are traveling, like let's say that you're going one direction that your del f is going, and let's say u is going that same way, then your angle will be 0. So that's when your magnitude of this thing is going to stay the magnitude of del f. So that's when you're going to be traveling at 5. I mean, you're going to be that velocity right there. Then if you go the opposite way, so if your angle is 180, so if you go away from del f, then you would still have a 5 here, but your cosine would be negative 1 because you're going 180 degrees in the opposite direction. So then your directional derivative would be negative 5, so it would be the smallest, right? So all I'm trying to do is like let you see here from this formula, like when is the magnitude the most? When is your derivative the most that it can be and the least that it can be? All right, so here we go. So the magnitude of del f is the maximum value of the directional derivative. So in other words, it is the maximum rate of change of the gradient. So in other words, where the velocity is the highest. All right, this occurs when u has the same direction, so remember u right here, has the same direction as the gradient vector, which is del f, okay? Therefore, the least rate of change, or the slowest, occurs when we go the opposite direction of u. For example, if theta was pi over 4, so like let's say that you were going in the pi over 4 direction, right? The opposite direction would be this way, so imagine that is 5 pi over 4. Okay, so it'd be the most, so it's the most when you go the same direction as del f. When del f and u are going the same direction, you get the biggest gradient. When del f and u are going in opposite directions, you get the least velocity. Okay, so this one here, let's see, where am I here? So find the rate of change of your function at the point 2, 0 in the direction from p to 1/2 and 2. So this right here is quite a bit you have to figure out right here. So my u, this is my u, right? This is the direction I'm going. I'm going from p to 1/2, 2. So I'm going from this point to this point. So I have to find that u vector. So u is going to be 1/2 minus 2, so that will be -3/2. And then 2 minus 0 is 2. So that's u. But remember, I have to make it into a unit vector, so I have to divide it by its own magnitude. So the magnitude would be 9/4 plus 4. So that would be 16 over 4 plus 9 over 4. That would be 25 over 4. So this guy over here is the square root of 25 over 4. So that's 5/2. So that's u equals -3/2 over 2 divided by 5/2, so times 2/5. So if I go ahead and figure that out, u is, let's see, the 2's cancel, I get -3/5, and I get 4/5. All right, so there's my u. It's a unit vector, and it's going in the direction from p to 1/2, 2. All right, so find the rate of change at 2, 0. All right, so A. So the rate of change, the directional derivative, all right? So that's what that means, and so I need fx. So my fx is going to be just e to the y. My fy is going to be x e to the y. I'm doing this at 2, 0. So plug in 0 for e to the y, I get 1. And plug in 2 and 0, so I get 2. Okay, so my du of f at 2, 0 is my del f. So del f is what we just found right here. So it's 1, 2, dotted with my u. So dotted, so -3, 5, and 4, 5. All right, so put those together. When you dot them out and multiply it together and add them up, you get 1. Okay, so letter B. Letter B says, in what direction does f have the maximum rate of change? And what is this maximum rate of change? So the direction to go to get the maximum rate of change is the same direction as del f. So in the direction of del f, we get the maximum velocity, or max rate of change. All right, so del f goes in the direction, del f was 1, 2. So how do you find that direction? So think of this. You go over 1, up 2. There's that vector, 1, 2, right? And so if you think of a little triangle right there, you've gone 1 and 2, you need this angle right here. So you're doing the tangent of that angle is 2 over 1, so inverse tangent of 2. So you get theta equals 63.4. So there's your direction right there. And you can also just say in the direction of del f, all right? And what is this maximum rate of change? Well, the maximum rate of change is the magnitude of del f, 1, 2. So that is the square root of 5. So this is the maximum velocity you're ever going to get, near the point, near the point 20, and it's going to be in the direction of del F, which is 63 degrees coming off of there. Okay. All right, so this is just another example that I had here. I have it all worked out so that you can see everything. So I did my 3 derivatives, tx, ty, tz. So I was doing the quotient rule. So the derivative of the top is, derivative of 80 is 0. So that was 0 for each little thing right here, okay? And then I did times the bottom, that would still be 0. Then I did the derivative of the bottom. So the derivative of the bottom with respect to x or y or z. So that's what you're seeing right here, here, and here. And then times the top, so there's the 80 in each case. And then the bottom, I had to do the bottom squared. So there it was, and it's the same on each one. So I had to plug in 1, 1, negative 2. So I did that, and so here's what I got. Okay, so that was del t, all right, because this one's called t instead of f. So that was a change in my temperature and my del t at that point. And my rate would be the magnitude of that thing. So I figured that out right here. And then basically it came out to about 4 degrees. Okay, so this is the maximum rate of increase, and it is in the same direction as del t. So it's in the same direction as this thing right here. And this is the maximum change in temperature that you would ever get in any direction, the direction that del t goes in. All right. So, tangent planes. So this is the last important part we have to do here. Here's a picture of what a tangent plane looks like. So we saw this before, and we knew how to make this before. So look at the direction of the gradient vector. So the gradient vector, that del F right there, is this guy right here, right? So the direction of the gradient vector is perpendicular to the tangent plane. Well, that's awesome, because when I make the equation of a plane, I want the normal vector, the thing that's perpendicular to the plane. And look at that, it already is. Yay! Okay. All right, so I got a plane, tangent plane at one point, tangent to the surface. All right, equation of a plane, so remember that from before. Okay, so to find the equation of the plane, the equation of a tangent plane to a level surface, basically we have to do this. Del F, or big F, little f, whichever, at the point x0, y0, the point that you're talking about, z0. All right, we dot this with x minus x0 and y minus y0 and z minus z0. Now, you're thinking, oh my gosh, another formula. Oops. But it's not really. You already know this. Okay? So, what we have to do, del F is going to be our direction, right? Our normal vector. And so, let's go ahead and find that here. So, let me find del F for this guy right here. I need x, y, and z. So, I need fx, fy, and fz. All right, so the derivative with respect to x of this problem would be y sine z. The derivative with respect to y would be x sine z. And the derivative with respect to z would be xy, and then derivative of sine is cosine. So xy cosine z. I have to do this at this point. So when I plug in those numbers and pi over 6 and stuff for the z, I'm going to get 1/2, and this guy is square root 3, okay? Because a sine at pi over 6 is 1/2, so I basically have 2 times 1/2, which is 1. The sine at pi over 6 is, again, 1/2, so I have 1 times 1/2, so 1/2. And here I have x times y, so 1 times 2 is 2, and the cosine at 1/2 is square root 3 over 2, so that's how I'm getting the square root 3. Okay, all right, so there is my directional derivative, and that is also my normal vector. So I got my normal vector 1/2 and radical 3. I dot this with x minus 1 comma, y minus 2, comma, z minus pi over 6. So look at what you're doing here. You're multiplying 1 by x minus 1 plus 1/2 times y minus 2 plus radical 3 times z minus pi over 6. And this is just the equation of a plane that you were always doing. Do you see? A, B, C, and then your x minus your point, y minus your point, z minus your point. Okay, so it's everything that you did before. And you can leave it like that, or let's clean it up a little bit. We're going to have x plus 1/2 y plus radical 3 with a z. This guy right here, this is going to make a -1. This is going to make another -1, so -2. And then this ugly thing right there. So we're going to have minus 2 minus radical 3 pi over 6. So, yeah, great. All right, so there's also a normal line to the surface. Okay, so you have a tangent line and a normal line. So remember, this is a line that is perpendicular to the tangent plane. Well, passing through the point being used. Now the trick is you already literally know the direction of this line. It's this thing right here. It's the normal vector that you already know. It is del f. So that's great. So if you have the equation of the tangent plane, the direction of that plane is its normal vector. So if you want a normal line, you just steal the equation, or you steal it from the from the plane equation. All right, so we're going to steal it right here. So we're going to show you that right here. So we're going to do the tangent plane. And it's the last one. Tangent plane, and we're going to do the normal line. All right, they're both using this point right here. So all I have to do is find my fx, fy, and fz. This is going to be my normal vector. Okay. All right, so fx. I'll be just looking at this part right here, so I'll get 2x over 4, so I'll have 1/2 x. Fy, I'll get that part, so it'll be 2y. And fz, well, that'll be 2/9 z. So plug in my numbers, -2, 1, and 3. Plug in -2 here, that gets me 1. Plug in 1 here, I get 2. Plug in -3 here, that gets me -2/3. And that right there is my normal vector at this point. Okay, so that means my tangent plane is going to be 1, 2, -2/3, dotted with x minus -2, y minus 1, and z plus 3. All right, so if I multiply that out, remember what happens when I get an equation of a plane, I can just put this in front of the x, y, z, so x plus 2y minus 2/3 z, and if I want to, I can just dot the point with my normal vector, and that is my value on the other side. So if I dot -2 with 1, I get -2, 1 with 2, I get plus 1, and -3 with 2/3, I get plus 2. So that would be 1. No, wait. Hang on a second. -2 plus 2, the middle is 2, sorry about that. And the last part is 3's cancel, so plus 2, yeah. All right, hang on a second. Did I write something now? 1, 2. Oh, crud. This was a -1. Sorry about that. I know you're probably telling me, oh, you made a mistake. All right. So anyway, this is -1. That means this is a positive 2. There we go. So that would be 6 on the other side. Okay. And my normal line, well, look, my vector for my line is -1, 2, and -2/3. My point is -2, 1, -3. And so I just make up an equation of a line. X equals, Y equals, Z equals. I would have -1t minus 2. So I'm using these two pieces of information. Then I would have 2t plus 1. Then I would have -2/3 t minus 3. And there's my normal line. And that, folks, is it. So remember, you are going to do half of these problems, so at least these 3, please. All right, I'll see you later.